welcome to episode 22 of your CYSA Plus Prepcast. In this session, we focus on the architectural backbone of secure network design and segmentation. Every system in an enterprise connects to some form of a network, whether it is a local office network, a distributed cloud infrastructure, or a hybrid of both. Understanding how those networks are designed, segmented, and secured is one of the most critical responsibilities of a cybersecurity analyst. In modern environments, attackers are no longer just targeting the perimeter. They're exploiting lateral movement opportunities, misconfigurations, and weak segmentation to spread rapidly once inside. That's why effective network architecture and segmentation strategies are vital to limiting damage, enhancing detection, and enabling fast, informed incident response. To begin, let's define what we mean by network architecture. At its core, network architecture refers to the structure and layout of a network, including how devices are interconnected, what communication protocols are in use, how traffic is routed, and what security controls are applied. It encompasses both the physical layout of cabling and hardware and the logical design of traffic flow and access policies. For analysts, understanding this structure means being able to identify how a threat entered, what it could access, and how to contain it. This foundation underpins nearly every decision an analyst makes during triage and investigation. Analysts must also be able to distinguish between various architecture types. Traditional on-premises architectures involve networks that are physically controlled by the organization. These include switches, routers, and firewalls located within data centers or office buildings. In these environments, analysts have deep visibility and direct control over traffic and access policies. They can implement hardware firewalls, use physical segmentation, and monitor traffic at multiple points. The exam may ask you to assess the security of an on-premises layout or recommend how to harden it. Cloud architecture, by contrast, places many infrastructure components in virtual environments managed by providers such as Amazon Web Services, Microsoft Azure, or Google Cloud. Analysts working in cloud environments must manage virtual networks, cloud-based firewalls, and identity access controls without the ability to physically segment traffic. Visibility often comes from logging tools provided by the cloud vendor and must be configured intentionally. Misconfigurations in cloud architectures can lead to devastating consequences. Public lacing storage buckets, open access to management consoles, or overly permissive IAM roles are all examples of cloud-specific risks that analysts must watch for. Hybrid architectures combine on-premises infrastructure with cloud resources. This is increasingly common as organizations retain legacy systems while adopting cloud services for scalability and flexibility. These environments present unique monitoring and segmentation challenges. Analysts must track data flows between local and cloud systems, ensure consistent access control policies across both environments, and monitor for cross-boundary threats. For instance, an attacker who compromises a local workstation might try to pivot into the cloud environment using reused credentials or unsecured API keys. You may see questions on the exam that require you to analyze the risks associated with hybrid infrastructure or identify missing security controls. A critical part of network security design is segmentation. Network segmentation involves dividing a larger network into smaller, logically isolated segments. The purpose is to limit the scope of access and reduce the attack surface. If an attacker gains access to one part of the network, segmentation ensures that the rest of the environment remains protected. Without segmentation, threats can move laterally, compromising multiple systems rapidly before detection. Segmentation is also used to apply policies at the segment level, monitor traffic more precisely, and meet compliance requirements for isolating sensitive data. There are several methods for implementing segmentation. One of the most common is the use of virtual local area networks, or VLANs. VLANs allow analysts to logically group devices, even if they are physically distributed across the network. By assigning devices to specific VLANs, you can limit broadcast traffic, reduce congestion, and isolate traffic for security or operational reasons. For example, guest devices may be placed on a VLAN that cannot access internal servers, while finance systems may be assigned to a VLAN with enhanced logging and restricted access. Analysts monitor VLAN traffic for anomalies, such as unexpected communication attempts between segments. Subnetting is another segmentation technique that involves dividing IP address ranges into smaller subnetworks. This is both a network design and security practice. Analysts can use subnetting to control how traffic moves between segments and to apply firewall rules at the subnet level. Subnets help analysts isolate compromised systems, enforce policy boundaries, and reduce the spread of malware or unauthorized access. You may see subnetting-based scenarios on the exam, including questions that ask you to calculate subnet ranges or determine appropriate segmentation based on organizational structure. Firewalls are critical in enforcing segmentation. Both perimeter and internal firewalls are used to control traffic between segments. Perimeter firewalls control access to and from the outside world, while internal firewalls restrict access between different internal systems or departments. Analysts must ensure that firewall rules are correctly configured, follow the principle of least privilege, and are updated regularly. Monitoring firewall logs helps analysts identify attempts to bypass access controls, communicate with command and control servers, or move laterally between segments. The principle of zero trust significantly strengthens segmentation strategies. In a zero trust model, no device or user is trusted by default, even if inside the network perimeter. Every access request must be authenticated, authorized, and validated. Segmentation in a zero trust network becomes more granular, with restrictions based on identity, role, device posture, and context. Analysts operating in zero-trust environments must manage and monitor these policies closely, ensuring that controls are enforced dynamically and in real time. For more cyber-related content and books, please check out cyberauthor.me. Also, there are more security courses on cybersecurity and more at baremetalcyber.com. Building on the foundation of segmentation and network structure, modern enterprise architectures continue to evolve, integrating cloud-centric models, mobile access, and identity-driven policies. These shifts demand that cybersecurity analysts not only understand static network layouts, but also the dynamic architectural patterns that adapt in real time to users, devices, and workloads. In this part of the episode, we'll examine several of the advanced architectural models and technologies analysts must master, all of which contribute to securing communication paths, enforcing access policies, and controlling movement across and within networks. One of the most transformative developments in modern network security is zero-trust architecture. As introduced earlier, zero trust eliminates the notion of inherent trust based on network location. Whether a user is in the office, on a corporate-issued device, or connecting through a trusted subnet, no access is granted without verification. Analysts working in a zero-trust model must enforce continuous validation of identities and devices, tightly manage access rights, and maintain segmented control over sensitive assets. In practice, this model requires strong authentication, device compliance checks, and the ability to revoke access quickly. The CYSA Plus exam may test your ability to implement segmentation in a zero-trust context, or evaluate which network design best supports zero-trust principles. Secure Access Service Edge, often abbreviated as SASE, builds on the concepts of zero-trust and cloud networking. SASE centralizes security and networking functions in the cloud, allowing organizations to enforce policies consistently across distributed users, devices, and applications. In a SASE environment, analysts monitor activity through a combination of cloud firewalls, data loss prevention systems, and secure web gateways, all delivered from the cloud edge. These services are identity-aware and location-agnostic, meaning access decisions are made based on user roles, device posture, and behavior rather than on fixed network location. Understanding SASE allows analysts to make sense of traffic patterns, logs, and alert contexts in highly mobile and decentralized environments. Software-defined networking, or SDN, is another advanced architectural model analysts must grasp. Traditional networks rely on fixed rules programmed into hardware appliances like routers and switches. SDN replaces that with centralized controllers that manage the entire network's behavior dynamically. This allows for faster policy changes, real-time segmentation, and more responsive threat mitigation. Analysts working in SDN environments must understand how traffic flows are controlled via software, how policies are applied to different virtual segments, and how SDN logs and telemetry can be used to detect anomalies. Exam scenarios might involve SDN traffic configurations or questions about how to contain a threat using SDN-based segmentation. Microsegmentation builds on traditional segmentation by applying controls at a much finer level, typically within data centers or cloud environments. Instead of separating departments or device classes, microsegmentation divides traffic and access at the workload or application level. Each application component can have its own firewall rules, access permissions, and monitoring policies. For analysts, this level of granularity offers significant security benefits. It limits lateral movement within the environment and allows for precise alerting and containment. However, it also increases complexity. You may be asked to identify when microsegmentation is appropriate or how to configure it without introducing policy conflicts. Network demilitarized zones, or DMZs, remain a staple in secure network design. These are isolated network segments placed between a trusted internal network and an untrusted external one, often the internet. Analysts monitor DMZs closely because they house public-facing systems like web servers, DNS servers, and email gateways. These are frequent targets of attack. The goal of the DMZ is to contain any compromise of these services and prevent attackers from moving into the internal network. Analysts must ensure that firewall rules properly restrict traffic from the DMZ to internal segments, and that monitoring is configured to detect attempts at privilege escalation or lateral movement. Another critical aspect of network architecture is secure communication. Traffic between segments, between users and systems, and across the internet must be encrypted to prevent eavesdropping and tampering. Analysts must understand protocols like IPsec for establishing secure VPN tunnels, SSL and TLS for remote command execution. Analysts also monitor for improperly configured encryption, such as outdated SSL versions, self-signed certificates, or unencrypted data transfers that can expose sensitive data. Expect exam questions to test your ability to recognize weak encryption implementations or to recommend secure alternatives. Monitoring segmented environments is vital to ensure that segmentation is functioning as intended. Analysts use a range of tools, including intrusion detection and prevention systems, anomaly detection platforms, and flow monitoring tools to observe traffic across segments. These tools help detect unusual communications, unauthorized access attempts, or policy violations. The complexity of segmented environments means that analysts must also monitor for misconfigurations, rules that are too permissive, alerts that are suppressed, or access controls that conflict with the intended architecture. Network Access Control, or NAC, enforces access policies at the point where devices attempt to join the network. NAC solutions can validate device health, enforce authentication, and quarantine devices that fail security checks. Analysts configure NAC policies to ensure that only known compliant devices can connect to sensitive network segments. NAC also helps analysts maintain an accurate inventory of devices and detect rogue hardware. On the CYSA Plus exam, you may encounter scenarios where NAC must be implemented to isolate a threat or to block unauthorized endpoint access. Penetration testing and vulnerability assessments are essential for validating network architecture. Even a well-designed segmentation plan may contain overlooked weaknesses. Analysts conduct regular assessments to identify open ports, misconfigured firewalls, unnecessary services, and unprotected access paths. These assessments help confirm that segmentation controls are working as intended and that sensitive assets remain isolated. The exam may present test results and ask you to identify which weaknesses undermine segmentation or how to remediate a discovered misconfiguration. Finally, documentation is one of the most underappreciated aspects of secure network architecture. Analysts must maintain clear and up-to-date network diagrams, access control matrices, and configuration records. This documentation helps analysts respond quickly during incidents, plan for infrastructure changes, and support audit requirements. When network topology is unclear or undocumented, even the best security tools can be undermined by confusion and delay. The CYSA Plus exam may challenge you to evaluate whether documentation supports effective response or identify missing components in a network diagram. To wrap up this episode, network architecture and segmentation are not just passive design choices. They are active, enforceable strategies that shape the way threats are contained, users are authenticated, and data is protected. Analysts who understand these strategies gain an operational advantage in detection, response, and prevention. Whether you are designing a zero-trust network, managing micro-segmentation in the cloud, or tuning firewall rules between VLANs, your knowledge of architecture design directly impacts your security outcomes. Continue building this knowledge through labs, configuration exercises, and architecture reviews to ensure full preparation for the CYSA Plus exam. Thanks for listening. To learn more about cybersecurity, please visit baremetalcyber.com. There you will find best-selling books, videos, and even more free cybersecurity training courses. Please subscribe to the Prepcast and our various podcasts. And thanks for listening.